But I think there'll be a decision made very quickly. I think he has to announce the candidate at the end by tonight. So I think you'll know very soon. Anyway, good. I see some people are here for 127. And I think a few minutes before we officially start here. So I just want to see if there's anything fun in the news. And there's still a few people clearing out from the previous class here. All right. So let me see what might be worth. Oh, this is worth mentioning. And
so CCBC training is happening today.
Yes, I'll be there. I'll open the lab for anybody who wants to do it here.
We're just going to be here for an hour then?
No, it goes from 2 to 5.
Right, but class here.
Oh, I don't know. Probably. But if people want to leave early to go to that, that's fine.
Okay.
But I'll stick around so you guys can stay on campus if you want to till 5.
Right. But my question is, if we're going to be, because this will be kind of our first CCTC meeting today, but if we are going to compete and we're going to be practicing on Saturdays, like from around this time.
Yeah, I don't know the answer to that. I don't know how often these. I don't really know. Yeah, I don't really know how often the training events are or anything. You'll have to ask these questions of Liz, but she probably doesn't know either right now.
Okay.
They just announced these trainings like a couple of days ago, and I don't think anybody knows what's going on.
Yesterday.
Yeah.
So, okay. Are you going to be a trainer or
no,
participating in any capacity?
No, probably not.
Okay.
No, it's Liz.
Okay.
Good. All right. Anyway, good. These are. What's that? Yeah, I don't know. It's up to you. I'm going to teach this class for about an hour, and then I'm going to grab something for you upstairs.
Okay.
I got a class to teach right now.
Sounds good.
Yeah. All right. Anyway, so.
Richarte, can you hear me? Okay, I'm sorry.
Let me mute folks. All right, there we are. All right, so DNS crypt is coming, apparently. Yeah, let me interrupt you guys. So DNS crypt is there. As we talked about before, your DNS queries go over unencrypted UDP and reveal a lot of your private browsing to everybody. And nobody has been interested in doing anything about this. Shut that door. Anyway, so there's 2 technologies to fix that problem: DNS crypt and DNS curve, and both of them have never made it past an early level of beta testing where there's no Windows client at all. The Linux clients crash all the time, and there's very few servers. So here's another one. Quad 9 is a new open DNS resolver, 9.9.9.9, and they now have a DNS crypt in testing. So I'll give it another shot and throw it in the DNS class if any of it works. In the past, I haven't found any version of DNS crypt or DNS curve that works well enough to even give students for projects, because they just crash half the time and don't work. It is, as far as I know, the only way to protect your DNS that is actually practical is to use a VPN, and 80% of the VPNs don't work right and they don't protect your DNS. So it is a gaping hole in privacy on the web right now. Almost everybody's DNS queries reveal everything they're doing. And maybe this will be a step towards fixing it.
Question.
Yeah.
Why can't you just do HTTPS to your DNS server?
That's a very good point, and I'm glad you brought it up. DNS over HTTPS is the newest and I think the strongest contender. And I know, and is there a good client for that? Last I heard, there was still no client available on Windows or anything. But that, I think, is probably the best answer. What happened is, around the time these protocols were proposed a long time ago, and HTTPS, I think, is the one that won. So running everything over HTTPS is probably a good plan. For example, DNSSEC is very strange and primitive. It uses primitive cryptography, really weird stuff like base 32 instead of base 64, because it's really old. And I think a lot of these protocols turn out to be unnecessarily out of date and redundant with HTTPS work.
It's kind of obvious because you can connect to a web server.
Yeah.
DNS is just another server. Well,
Well, you can't get to a normal HTTPS. Yeah, you're right. You're right. Anyway, Google offers, I think Google offers DNS over HTTPS. And I think Burp uses it by default. And that would be my vote for something to build into a browser. But I got to look into it again. Last time I looked, a year or two ago, none of these things were actually, usable for them. Yeah. It's a good question. Technically, it will be slower, of course. It'll be more exchange to set it up and more processing time and network time. And that was what a lot of people used to get real upset about. That's why they wanted DNS to go over UDP instead of TCP to make it faster. I think now that's not as big an issue. DNS is really old, and it was designed for really old generations of hardware. I don't think those concerns need to matter so much anymore. But yeah, it's a big issue.
It would be TCP at that point, right?
What's that?
It would have to be TCP if it was secured, right?
Yes, of course. And not only TCP, but encrypted. So a higher handshake and everything. And I think that's fine with modern equipment. I think that 20 years ago or 30 years ago when it all started, they regarded the performance penalty as prohibitive.
For scanning, that would be an issue.
For scanning?
Yeah. They use UDP for DNS scanning on networks and stuff, and that does.
Well, sure. Yeah, Nmap, but I mean, Nmap just uses whatever is the common protocol to get in. Anyway, it looks like we're about to the right time. I don't think we need to worry about this stuff. Yeah, we're good enough. So let's talk about format strings, because this is good, clean fun. And once again, it's another category of vulnerability caused by C. And actually, one thing I've never found a good answer to is why C does this bizarre thing. Buffer overflows, at least, are understandable because C has to reserve space for a variable, and it is in the interests of efficiency that it does not check later when you use it to make sure that you only use the space you reserved. That I at least understand. It would be more complicated to fix it. This is just bizarre. And it goes like this. When you print something from C, the fundamental issue here is the same thing we've been dealing with all along, which is that your computer does not know what it's doing. It's just manipulating bytes without understanding them, like someone who, say, memorizes words in a language they don't understand and then they recite them because they're an actor. So it doesn't know whether your byte is an integer, an instruction, an address, a movie. Bytes are just bytes. So you can feed it data that it thinks is a URL or a password, and then later on tell it to interpret that data as code to be executed, and this can work. And so here, we're going to mess with the format string. And the format string is one important example of this. Let me bring it up here. If I go into 127 and chapter 4. All right, I'm going to make this big. Okay, so the first one here, I've got, format string examples. Okay. All right. Okay. So let me get rid of the colors and make it big. All right, so what I've done here, I've made a character, okay, this is an integer with 1001. Here's a character with 65, which is a capital A. Here's an array of 10 characters, which is a string. And then I do a string copy into that array of hello, and it will add a null byte to the end. So now I have three kinds of variables. You can print out the integer with %d or %x. %d means print it as a decimal number. That's normally what you want. %5d means make it a decimal number, but pad it out to a total length of 5. %x means print it in hexadecimal, and 5x pads it out to a length of 5 in hexadecimal. And this, you can print the same thing each way. Characters can be a C for a single character or an S for a string. Now the string is an optional data type, and you have to bring it in with this include statement. A string means you're going to have a pointer to the first element, and it will interpret the string as including all the characters from that point on until it hits a null byte. This string copy operation puts in the 5 characters, HELLO, and then a null byte. So this is now going to know how much to print. But the actual variable H contains a pointer, 32 bits, to the start of the string. And when you feed it to the print statement, it interprets this H as a pointer, and the %s format tells it to print the string that pointer points to. Here I print the same thing with %p, and that will print the value of the pointer, not the string. And so this is what they call indirect addressing. The actual thing stored in H is a pointer to it, and this is why you have buffer overflows. The actual way C stores a string is it stores a pointer to the start of it, and the length is not stored anywhere. The length was defined up here when you define space for the string, but all it really knows is the pointer. So when it comes down to, say, copying data into it, it has no way to tell how big it is. This is a strange design decision made by C. Pascal did not do it this way. Pascal stored strings where the first byte is the length of the string, and after that come all the bytes. So you always know how long it should be. So in Pascal, it would be much easier for the compiler to avoid an overflow because it would know. This idea of having a null terminator at the end to determine the end of a string leads to a lot of weird problems, one of which is if you accidentally overwrite the null terminator, then the string will just continue to include all sorts of bytes that were never included in the string. And there are some C string copy operations that do not put the null byte in, and you have to know that. And if you don't put it in yourself, when you copy strings, you'll end up with a weird mess that has extra junk at the end. Anyway, but here's the one that's really going to get to us, and I'll come back to that. So let me run this program, string examples. Okay, what's going on here? Oh, format string examples. All right, so if I run it, what you see, I'm moving it up on my screen if I can only get hold of it. There. All right, so here's a integer, here's a 5-digit integer, here's a hex value of it, and here's the 5-digit hex value of it, just 2 spaces at the start. This is a character, and this is a string. This is the same variable printed with %p, so this is the pointer to the string. Now, if you get used to this stuff, you can see it's on the stack. BFFF is where the stack is. You'll get used to seeing that as we do our exploits. Now, what happened here is I'm seeing a lot of weird numbers, and if you look at the code, let me put the, okay, let's get rid of all this nonsense. Okay, all right. The last one is the one that's going to lead to all our trouble here. You can print with a format string and no data to print. This is, again, a problem with C and ultimately a problem with assembly language. Remember, we talked about what function calls look like in assembly language. If you're going to call something like print, you push arguments onto the stack, then you call the subroutine. It looks on the stack to find your arguments. You can call it without putting the arguments on the stack first. And because C is so stupid, it will run the function and look on the stack and assume that whatever is there is what you put there. Because it doesn't have any of this checking. It's the same kind of failure to question orders that you get when it says, take a string that's only 10 characters long and put 100 characters there. It says, yes, sir, I would never question your orders. I'll start here and write next 100 characters, because it doesn't try to guess what you're doing and make sure that what you're doing makes sense. It's only trying to see if I can take this one line of C and turn it into an assembly language command. And if I can, it just does it and asks no further questions. C will only complain when you are so wrong that it cannot even understand what you're trying to say. Like if you forget the semicolon, and it says, I don't even know where this command ends, I can't make a line of assembly. So you tell it, call the print statement, and print the first 3 things you see as hexadecimal numbers, and it will do that cheerfully, even though you did not put those numbers on the stack. So what happens is, it prints out whatever happens to be on the stack. So these are just random numbers that happen to be there. Numbers that were left over from earlier processes. So this is information disclosure vulnerability. I can now read things that I did not put there. And so that's the first consequence of this. Yeah.
Kind of stuff, or most of these things through C, C++, and C#.
Yes. I think, as far as I know, the later versions C++ and C# do not fix these problems. Although I cannot speak from experience. I've only done it for C and C++. I know C++ does not fix them. And I don't think any later version of C does either, because they consider this to be part of its efficiency. It is the programmer's obligation to think of these things, and therefore the programmer can use these things. You can very carefully reserve a space and then in other ways control the next 10 bytes and then refer to those 10 bytes. It wouldn't assume that you're only going to do it the one official way. That's the point. You're supposed to be able to be super brilliant and think of some cute binary trick to make things great. by trusting these operations to do exactly what they claim to do and no more.
I could sit in the C++ class and go, oh, goody, if I need to add something, I can use some of this.
Yes?
There are some advantages to it depending on your goals.
Yes, of course. And that's the C and Unix are both designed by sort of mathematicians, where it does one binary operation and that's it. It doesn't then try to guess what you meant and only do it under certain conditions. It does exactly that. And therefore, it's a tool you can use. And they don't worry about the fact that there's a common error you could make. They just make sure that it mathematically does what it's supposed to do. And that's Microsoft is exactly the opposite. If you take a language like PowerShell or Microsoft domain controllers and control them through the GUI, they're all full of business commands that perform a business operation. That's why there's 10 different ways to do the same thing, and none of them are like mathematically simple or pure. They are designed to do exactly what a business person would expect it to do with the expected constraints, whereas Unix and C are designed by like logical mathematical people to do the binary act that you're doing. And so they would say, I was copying a string. I was not checking length. That would be a different function. Copying a string just means copy until you hit the null byte. That's it. Argue with you because you really shouldn't have asked me to do that is not in my, anywhere in the specs. Quite the opposite. It should always do exactly what it says it's going to do and never stop and argue with me because of extraneous details. It's a fundamental philosophy, like the open source philosophy that some people have, that everything has to be public and open source. Anyway, so this means I can run this. So let's have a format string vulnerability. If I do fs.c, here's an example of something that will take input from the user here in the argument string. So it's going to take argv1, which is the name of the program followed by an argument. It's going to take whatever it finds there, copy it into a variable called buff, which is 1024 bytes long, and then print it. Now this, by the way, has a buffer overflow vulnerability, same kind we've had before. It didn't check the length of this. So one way to exploit this would be to put in more than 1,000 characters in the command line argument, and that would work. And we could do that, but that was the last chapter. Now we're going to exploit another vulnerability it has, which is this print has no format string. Now, again, C allows you to do this. If you want to print something out and you don't care how it looks, like it's a diagnostic message, I just want to see it, you do not have to specify the format string. C will guess what format string to use. So it'll print out the value of that buffer, which is okay, normally. The problem is you could put format commands in that buffer and it will now interpret them as format commands because it doesn't know. It will just take the stuff on there, the things it finds on the stack as instructions. So let's run this one. This is fs. If you run fs with no argument, it will crash because I didn't handle the case with no argument. If I give it an argument of like hello, then it will just print out hello because it sends that string to the printf command, and this string is just fixed text. It prints the fixed text and it doesn't have any format specifiers, so it doesn't look for another argument to print there. But if I give it a format specifier, like %x, 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 now it's going to print this string. It's going to see that these are format specifiers, and it's going to look further down the stack for more variables to put in there. So it's going to print numbers that it fetched from higher on the stack, which I didn't put there. And I can have as much as I want here. I can put a separator like a dot in here, and I can just keep going. And now I've got the next 4 words on the stack, and I could go hundreds or thousands. I could even use specifiers with a dollars number, which skips over a bunch of entries on the stack. I can now read from this point in memory forward until I hit the end of the segment. I can read anything I want off the stack and see it here. So that's disturbing. And by the way, another nutty thing you could do is you could put a %s here, and now it will try to print. If it finds anything that's a string, it would try to print it. If any of these were pointers to strings, I think you could perhaps print things out that way. But normally you settle for %x. So that's the first thing. Now we've got an information disclosure vulnerability where I can see things that the programmer did not expect me to be able to see. But you can do much worse because of this bizarre thing called the %n specifier. If I put in 2%ns, I get a segfault. I have no idea why this exists, but the %n format writes to memory. it takes the next number on the stack, the next argument, and interprets it as a pointer, and it writes to that address. Now, I don't know why you would want that, because what it writes is, in fact, a number equal to the number of characters that have been printed so far. I have no idea what the point of this was. But now what this means, here I can read from arbitrary memory, and here I can write to arbitrary memory, right from the format string. So it's bloody awesome. And of course, if I can write to arbitrary memory, it's trivial to take over the machine, and that's what we're going to do. So they've been written in this print command. That's what's weird. I can write, but the number I put in there is inconvenient to control. It's equal to the number of bytes I've printed so far. It turns out to be possible to control, but it's inconvenient. So let's start. You control it by printing extra things long enough to make the total number add up to the number you want. So you'll end up having to print a couple of thousand characters to make it work. Yeah.
So it can write anywhere on the memory?
Yes, anywhere it's allowed to go.
It's allowed.
Anywhere, you cannot go outside your memory segment. So you'll hit a segmentation error, but I can certainly write anywhere on the stack.
Okay, I see.
Yeah, that's
So
a,
there's no privilege restriction.
that's right. There's no privilege restriction. It does have to be writable memory. And you'll see it more clearly when we get to Windows, but each memory, there are privileges in memory. You allocate a section and you define whether it's going to be executable, readable, or writable. And so it would have to be writable or it won't let you write. Yeah.
So generally we have address in like 80s. So if you were to do %x, then %n, would it then write into that because it pops the first two off the stack?
Yes. Every one you print, every argument you print is taken off the stack. So if I did %x, %x, %n, it would print the first two values and take the third value as an address and write to it. So you can mix reading and writing in the same command, and that's what you must do for this attack, because you must print enough to make the total number of characters reach the desired outcome, and then write that number to the desired address. Yeah.
If you were to combine this with Spectre and Meltdown, you'd get around the privilege restriction.
Yes, absolutely. A Spectre and Meltdown are one of the ways you get around that privilege exception. Another way, which we'll do when we get to Windows, is return-oriented programming, where you use the existing code with a ROP chain to turn off the privileges. Yes, but there are plenty of ways to get around essentially privilege escalation, ways to adjust the privileges so they no longer block you. Yeah, very good. People are right on track. So these are the ones that are important for us. %x is hexadecimal, and %number(x) is hexadecimal padded out to any number of characters, and that's of course what we're going to use to control the number of characters to make it add up to the right amount. And so here's the buffer overflow, right? I define a room for 10 characters, and then I copy more than 10 characters in, and C does it because when it's doing the string copy command, it has forgotten the name 10 command and in no way recorded that, so it has to worry about the fact that there's only supposed to be 10 the next time. And the format string without arguments is just the same. I have the string. It will now just, this one will just look on the stack and take the next 4 values and print them out in hex. So here's the one I controlled. Now, the %n will now write 2 numbers to the RAM with addresses from the stack, and the second one happened to be something that crashed the machine. So, all right. By the way, this affects all the variations of the printf function. There are about 10 of them in C that all work essentially the same way, and they all have this vulnerability. So if you want to prevent this nonsense, by the way, the defenses that protect you against buffer overflows will do you no good at all. Non-executable code doesn't matter. Address space layout randomization does nothing. The canary value at the end of the stack doesn't matter because you're not overflowing a variable. You're not overwriting the stack. The only thing that's going to do it is looking at your source code. Looking at your source code, it's blindingly obvious that you print something without a format string. So you could find it with just grepping your source code or any kind of source code syntax checker, but GCC will typically not warn you or prevent it. It is legal to print something without specifying the format. It is your responsibility to make sure that what you're printing under those circumstances is not controlled by the attacker, just like so many things. So now it's just a question of technique, and the technique is a little bit clumsy because it turns out that we have to write 4 times to make a word. We have to write 1 byte at a time. So here's the plan though. We're going to control a write operation. Now, the next question is, if I can only do a write, how do I take over the machine? With buffer overflows, I control the EIP directly. It's not immediately obvious how you can turn write into control the EIP, but it is pretty easy. You have to find a number which will eventually be put in the EIP later and write on there. And there are a bunch of those that will do that. So we're gonna do that. And so we'll find a target RAM location that will be copied to EIP, write the bytes there, and then make them point to our NOP code and NOP sled and shellcode, which we inject somewhere, and that's how we're going to do it. So the first question is, how do I control that address? And now this is a part, I remember when I first learned about format strings, it was hard for me to understand this point. But the point is, this data, when you run a command and you put a parameter here in the command line, that parameter goes on the stack. The operating system, bash, Unix, is going to take that, put it on the stack, and then call this fs function. So this data is on the stack. And it's the same data that the data those %x's are pointing to is the same stack that they're on. So the format string itself can be printed by the format string disclosure. It's on the stack. So what you do, let me go back to my example here. So I ran this one here where I printed 4 values on the stack. If I put some normal data in here as well, if I put, say, 4 A's here, then I'll see them here. Those A's are on the stack. In fact, they're the 4th word on the stack. So I'm here they are on the stack, and the 4th %x points to them, and I'm printing them. So this is how I control what I'm doing. I put a word here, and the 4th parameter after that points to that word. So if I put an address here instead of A's, and I put an N there, it's going to write to that address. So I control the destination in this fashion. Yeah.
So the writing example up there, 25 is %, and then 2UX.
Yes, exactly. The 25.2E7, this is %x dot. That's what this is. 25, yes. That's what it is. Now that I know how to control the address and write to the address, now I can make an attack as long as I choose a good address to attack to. And of course, here's some options. You could figure out where on the stack a saved return pointer is and point to that and then have it returned like a buffer overflow exploit. It turns out the easiest thing is a global offset table. That's what we're going to use here. This is the pointers that point to C library routines. You can also use something called the destructors table. When you launch code, especially in object-oriented languages, but to some extent also in plain C, it creates things with constructors, and when you leave, it destroys them with destructors. And it's just something called at the end. There's also hooks for C libraries you can use, and there's something called an @exit structure, which is called when you exit from routine. You can overwrite any of these things with the address you want, and you will eventually gain control of the machine. In Windows, there's one called the exception handler. And you could write to that RAM, and then when you cause an exception by doing something illegal, it will call them, and that will again put it in there. So there are many places where a write can turn into control of the EIP. What we're going to do here is use put char. So let me do, let me disassemble my program. Okay, oops, didn't listen to my -q. And it's not listening to my up and down. What's going on here? All right, lost, all right. What is going on here? All right. So if I GDB -q, whoa, something is fabulously not working about my computer. Let me see if I can find out what it is. Now this is working. Somehow I'm not getting any response from my command prompt. All right, I'm just going, let's quit. Okay, I'm going to close this and try reconnecting with a new terminal because I'm getting weird garbage instead of proper terminal response. All right. Okay, let's see if this is going to work. CD 127, that's working now. Okay, chapter 4. Okay, so if I GDB -q fs. Okay, so here's my program. I can disassemble main. Okay, and This is all preliminary stuff, preparing the stack in the prologue, and this thunk thing is also boilerplate. Here's that string copy. Remember how this worked. I read something from the command line, and then I copied it into a buffer. Then I'm going to print it. So this is the string copy. And if I go down further, here's the printf, which is the actual point of the exploit. This is the printf that doesn't have a format string. And then there's a put char after that to print out a carriage return, and that's it. So the printf here gives me a chance to override addresses, and then later on it's going to call the put char command to print this. So what I can do is use the printf to change the address that it thinks points to put char. And that is going to turn out to be pretty easy. Notice this put char at PLT. That is the procedure linkage table that is used to go to C commands. We talked about this before. When you call a C library routine, you do not jump directly to it. You jump to a table, a procedure linkage table in your code, and then you jump to a global offset table outside your code, which finds it. And this is because you share libraries, so you don't know where that library is. Each process doesn't know until it's running, so it jumps through indirection pointers to find it, and I can write on those indirection pointers, and you can see them. It's going to go to that address, 0x804. I can examine the code at that address. We will often dump out code in hex, but if you're going to call that as an executable instruction, I want to dump it out as readable instructions. So that's x1i at that address. So at this point, it's going to call that address, and what's at that address is a jump to this address, 804A018. And what's at that address, if I x1x 0x804A018, what's at that address is a pointer to the real C library routine. So when I try to print a character, first I go to the procedure linkage table, where I find a jump command, which sends me to the global offset table, which sends me to the library routine. So if I write here, I will hijack execution of put char, and it will run my code instead of the real put char. So now I know where I want to write. I want to write to this address. Now, I'm on the right track. Let me open up another window so I can have GDB open all the time. And go to 127, chapter 4. No, didn't. All right, what's going on here? All right. Okay. Okay. So I can now make an exploit. And I'm going to blow this up, and I think it's probably going to be F1. Okay, so here's my first exploit. I just take that address, 0804A018, and I make a format string that is %x, 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 %n, and then I print that stuff plus the format string. So this is going where my 4 capital A's did. The 3% X's are necessary to get down to the one I injected, and now it's going to print with the %n format the data I fed in. So it's going to write on that pointer. So this should give me control of the machine. It should give me control of the EIP, to be more precise. So let's take a look at that. That is f1.py. If I go here, I can run. Well, first, let's put in a breakpoint. You can see up here, this is where the exploit is going to happen, at that printf command. So let's break at main plus 76. So after the print command has executed and it has done something to memory, I'm going to stop executing so I can look and see what happens. Because very likely when I continue, it's going to crash. So I'm going to put a break at main plus 76. Okay, and now I'm going to run, and I want it to take data from that f1.py command. So it's going to take the Python code I just showed you and send that data to the command and run. Now it's going to break. Now, I believe I have overwritten this value, so I want to examine that value, 804A110. So I'm going to x, 1x at that value, and that's what happened. Remember, this value used to have a real pointer to a C routine, which is 08048366, but now it contains 1B, a real small number, less than 32, which is equal to the number of characters printed so far. So this is the format string vulnerability in action. The string here produced by the Python script has written here And what it's written is the total number of characters printed so far, which is 28 or something like that, 1B. So now I've gained control of the instruction pointer. If I continue this code, it's going to crash with an instruction pointer of 1B. This number is copied into the instruction point later. So now I control the instruction pointer, sort of. But I'm putting in stupid numbers that's causing a crash. So the next trick is how to control that number better. So let's take a look at f2.py. All right, so there's a couple of problems here. The first one is, if I don't want to print 4 billion characters, I can't make a real 32-bit number equal to the number of characters printed so far. So in order to get around that, I'm going to do 4 write operations. I'm going to write 18, 19, 1A, and 1B. So I'm only going to write the lower byte. So this way, I'm only going to need maybe 256 characters to hit anything I want here, and another 256 to control this one and this one and this one. So total number of characters printed is going to be only about 1,000, which is less mind-boggling. And so now if I do this, it's going to print %x, 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 %n, 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 %n. So it's going to take the first word I put on the stack and print to it, and then the next and the next and the next. I can do this as many times as I like. Because I increment it one by one, it's going to print 32 bits starting at this address, and then 32 bits starting at this address, and this, and this. So after 4 write operations, I will have written 4 bytes plus some collateral damage messing up the next word. So let's see what this one does. That is F2. And I'll start again. Okay, now if I look at what it did, it print 27, 27, 27, 27. Because if I bring it back here, and I'm going to shrink it up so I can see these two things at once. All right, what it did was it printed with the %n. The %n wrote to memory, but it did not print any more characters to the console. So the total number of characters printed so far did not change. So I wrote the same thing 4 times. And what I wrote was 00000027. So the first time I wrote, this was going to contain 00000027. The next time, it'll put the 27 here and have 3 zeros on the left, next one here, next one here. So when I'm done, I filled it with 27, 27, 27, 27. So I'm still putting in a stupid number that's going to make the machine crash, but at least I control all 4 bytes now. So as you can see, there's just going to be a few steps to get further here. Now I just have to refine this a little more. If I go to F3, now, if I want to print a different number to each place, then I'm going to have to print to %n and then print normal stuff for a while to change the total, and then print to %n again. So I'm going to have a pointer to where I want to write, and then a real variable to print, and then a pointer, and then a real variable to print. These B's are just placeholders, but they have to be there, so it has something to print. So this is going to print the first one, and then add 16 more characters to print the next one, 16 more characters in the next one, and so on. So they're now going to be different. So that's F3, and if I run that one here, I think I might be able to just shrink this and fit it on the screen at the same time. Be sort of fun. All right, there. So if I run F3, and then I examine what that did, that printed 37, 47, 57, 67, because this is hexadecimal. So this number, then I print 16 extra characters, so this number is 16 larger. Then I print another 16, so this number is 16 larger. And you can see we're getting closer to having real control of those bytes. So the next one, I think, gives us control of those bytes, which is F4. And now what I want to do here is print all zeros. That was my goal here. So to get rid of zeros, I discovered that subtracting 30 here did it. First, I tried subtracting 37 and it was off by something, and I wasn't interested in really understanding why. I just went by trial and error until I managed to get the number that caused it to be 0. Then I add 256 more characters in between, which will wrap around. And so I define these numbers, and when I print %x, %x, and then this n1 x's, and %n, then n2 x's and %n, n3 and n4, where n1, n2, and n3 and n4 are numbers between 0 and 256. So these numbers are going to set the first one to 0 and all the rest also to 0. So now I should be able to write a byte that includes nothing but zeros. and that's F4. So I run that. And now I'm able to put zeros in every byte. And remember, I've also wiped out 3 bytes of the next word as collateral damage, and I don't care because I'm only trying to gain control of the extended instruction pointer. And like all of our exploits in this class so far, all of these are doing collateral damage and will cause a crash later, which we could prevent, but it's too much hassle. That would be productive, useful programming instead of hacking. We're breaking into things here, which is why it's fun, because we don't really have to worry about cleaning up the mess we create very much, which is kind of tedious. So anyway, so the next one is to control that value entirely, and that's here. So again, you have a series of pointers that point 1 byte at the first byte, of lowest order byte of the word, and then each of the 3 bytes after that. So you do them one by one, and now I'm going to choose targeted values. And just for the first one, I'm going to use AA, BB, CC, and DD for the 4 targeted values. Now, the first one is A1 plus what I had before. Next one is A2 plus this minus some junk, A3. Those are the values that will result in the total number of characters printed up to that point equal to my chosen values, A1, A2, A3, and A4, plus some multiple of 256, which will wrap around to the extra byte that I don't care about. That's the kind of structure you need to write arbitrary values. So that's F5. And if I do this one, now I get AA, BB, CC, DD. So now I can hit any address I want. I'm about ready to finish the job here. Now all I have to do is put in a NOP sled and shellcode and find out where it is and point to it. So as usual, I'm going to start with a fake attack to make sure things are working. So first I leave this at a fake address, AA, BB, CC, DD, because I do not know what address I want to put in yet. First I have to load memory up and figure out where it is. So I need attack, and that's down here. I'll put in 100 bytes of NOP sled and 400 bytes of break. That's my dummy attack, just to use up the space in memory so I can find it. So now I print out the four words which point to the thing I want to overwrite, then the format string that controls it, and then the NOP sled and the buffer after that. So I'm putting my exploit right on the stack. Yeah?
Is there a limit to how many NOP sled you can have, like 200?
Yes. The question is there a limit to how big the NOP sled can be? Yes. The limit is ultimately the segment. Once you run out of this memory segment, you'll get segmentation errors. And if you go outside the reserved area of the stack, you'll begin intruding on other parts of the stack that aren't reserved here, and that may lead to other consequences. So it depends on your code. It depends on, and so often you get a very small region of bytes you can inject, like just 4 or 8 bytes. And therefore you can't put in a big attack. All you can put in is like a jump to somewhere else where you find more room. That's a big issue. In this case, the original program, I reserved 1024 bytes on the stack. So I can go up to 1,000 bytes.
Right.
And I did that for this reason, so I wouldn't have to worry about the complexity of hitting limits. Otherwise, I might have to find a much shorter exploit or use another layer of indirection. Good. So this one, if I run this one, this is F6. Let's say no and run F6. Okay, say yes. Okay, now it has printed all this junk. Now if I examine this, I'm going to find, of course, AA, BB, CC, DD, which I put there, but that's not very exciting. What really matters is the memory layout here. So let's do the same old stuff we've always done before. Info registers will show you that the stack begins at EFF0 and it goes to F4, so it's more than 400 hex big, which is 1024, which is why I say I gave myself some room here, so I know I can put in stuff. So let's examine, say, 60 words starting at ESP. And you'll see, here's my NOP sled, here's the start of my attack. So I gain control of the instruction pointer and I have to hit my NOP sled. So any of these values will do. All you need to do is find a value there that doesn't have any forbidden characters like 00, and I can put it in. So let me take a look at what I put in my other one. I think I chose a value here. Okay, the value I chose was BFFF06C. And take a look at the other window, and you'll see that 6C is here. That's in the NOP sled. I might have chosen one ending in 0, but I was an earlier stage of the attack. My things were wrapping around differently. This seemed more natural, but any value in the NOP sled will work. So I want to inject that address, and then I should be able to slide through my NOP sled and hit the brake. So that would be this attack here, F7. That's what goes to BFFF06C, and otherwise it's the same. So if I run F7, yes, and then I examine that value, it now contains BFFFF06C, which is going to hit my NOP sled. So if I continue, it's going to slide down to BFFFF0A5 and then hit a breakpoint trap. And now if I want to see that, I can see it up here before. So I jumped in to 6C, and I slid down the sled to A5. So I started here, and I went down to A5. That's what I did. So I hit the 6C here, went through all these NOPs, and then I hit the brake right there at A5. So it worked. I was able to execute the NOPs, and I was able to execute the first brake. And the first brake broke the program. So now I have verified that I can find my stuff, I can run code I put there, and all I have to do is make a proper attack. So we've done this before. Let me go back to my slides. These are all here for people who learned. So here's, by the way, I found in the debugger, I found the location to attack by just following these steps. You could also find it offline with the objdump -r command. Objdump prints out the contents. You can use objdump -d to disassemble the code, and there are other switches. The R gives you the global relocation table, and it shows you where things are. You can see the put char routine is at that address. It shows you all the C library functions you're using and where they are. So you could target any of them. You just need to find some C library function that is used after the printf and one that you don't mind destroying. If there's some function like there's one of the problems you have in homework, you actually want to print you win. So if you trash print, it'll never be able to print you win. You're going to have to target something else. So remember, you do collateral damage with these attacks. Now, if we were really cool, we could make an attack which cleans up after itself, and after it does my hijacking thing, it then calls the real put char. That would be really cool. I mean, that's what real rootkits do. They add functionality without breaking the existing functionality, but slobs like us, we're just breaking things to get in. Yeah?
Do the values of the dynamic offset change?
Yes, the location of the offset table does change, I think, depending on when you compile your code, but I haven't tested it very much. It's certainly not the same all the time. It certainly depends on your Unix version and stuff. Whether it depends on the size of your code or anything, I'm not really sure. It's a good question. I know it depends on how you compile it. You may notice back at the beginning, I compiled my code here with the -no-pi and the -z exec stack options. The no-pi put the code in this traditional old-fashioned location 0804. If you don't put in the no-pi option, it'll put your code all at 0000 because it's intended to be relocated later as a position-independent executable, and that will follow up all the attacks we're doing here. And the Z exec stack option made it possible to execute code on the stack. Otherwise, we would not be able to execute code on the stack, which is the default state now, and we would have to use a more advanced return-oriented programming technique to get execution, which we're going to do later, but I didn't want to worry about it yet. So with the -z exec stack option and the no-pi option, we're compiling things the way it was done about 15 years ago, which is when this original stuff was all developed. These are good questions. Anyway, so we target the GLT, we write to it, and that gives us control of the EIP. Then we write 4 bytes, but they're all the same by just having %n, 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 %n. To make them different, you have to print something in between with %n, %16x. And to make them under complete control, you have to calculate these extra bytes to print in the middle and then print them. And then you can hit any word you want. I can now hit AA, BB, CC, DD, which we did. And so then when we put in a fake attack of 100 NOPs and 400 CCs, we can find it in the debugger, target it, and slide down it and hit the breakpoint trap. So this is how to get us where we are. So the only thing to finish the attack is to get real shellcode. So you get that Oh yeah, I forgot. We might as well not skip over this like I have been doing. This is one step that people often skip over in textbooks, which is very annoying. Let's find out which characters are bad. Let me do this one live at F8. So we want to make real shellcode and take over the box, but in order to run inject shellcode, we're going to be making it with MSF Venom, and it might not be able to use all the characters. So to find out which characters are legal,
Hello.
you go down here, and for your shellcode, you put in characters you choose here. I'm going to take this back to where I started, which was, I always know 0 is no good. 0 will terminate C strings, so I can never use that. But I might be able to use 1. So let's go from 1 to 256. And this is in hexadecimal 1, but that's all right. So this will now print for a buffer. It's going to use 255 characters, or yeah, from 1 to 255, because a Python 4 string goes to 1 below the one at the end. So let's try this. It's going to send 255 characters up. That's F8. So if I run this one, F8, okay, yes. And now I just want to examine the memory, 60, actually in my up arrow list probably, there, this one. All right, so here's the NOP sled. Here's the actual attack coming in, 1, 2, 3, 4, 5, 6, 7, 8, and 9 never gets there. That's because 9 is tab. Null terminates the string, tab terminates the argument in a command line argument in bash, so it is interpreted as no longer part of this parameter, and it doesn't get there. So 9 is a bad character. I have to not use 9. So I have to check this again. So I know that I can't use 0 or 9. And to find out what I can use beyond 9, let's pick up at 10, which is A in hex, that'll do. Let's see how far I can get with 10. If I go to here and run it again, and then print this out. Okay, my NOP sled went in, then I printed a 10, and the 10 never got there. 10 is something like character return or line feed. That's also the end. So 9 is no good, and 10 is no good, and 0 is no good.
11 is no good.
I got to try again. If I pick up at the next letter, which is B, I should be able to get a little further. Okay, now I have my NOP sled, and here they come, B, C, D, E, F, 0, 1, 12, F, 10, 11, 12. It's working just fine up to 1E, 1F, and then 20 is no good, because 20 is 32, which is space, and space terminates the argument. So now I've got a list of characters I cannot use, which is 0, 7, was it 7, right? 7, 10, 9, and 10. 9 and 10, and 32 in base 10. Those are all characters I cannot use in my attack. And in hexadecimal, it's 0, 9, A,
You're tired.
and 2, 0, 20. Those are the hexadecimal bytes that must be removed from my shellcode. So,
Here, I gotta go down to the other end of the wharf. Can you have one?
Oh, and by the way, I should check. Since I found out that 20 was bad, I should see if there's anything above 20. There isn't, but I want to verify it. So if I go back to my loop and I start at 20, 0x20, 21, there. I start at 21 and go to the end. All right, let's see, I got a chat message coming in. Is somebody's mic on? Oh, I don't know, but I can probably mute people again. Let me give it a shot. I can mute everyone again. All right, so good. We'll see if that anything's any better. Richard, perhaps? Okay, anyway. All right, I muted everybody. I hope that helps. Apparently, good. Okay, good. All right, so here I'm 21 from 256. So I save that. And then I go here, run that. Yes. Examine the stack now. And you see, here's the NOP sled. Here's 21, 22, 23, and it made it down to 31, 41, 51. And if I go further, 61 up to F1, right up to FC, FD, EF. So everything from 21 to FF is okay. So now I know those are the only 4 bad bytes I have to dodge. Let's see if there's more chat messages here. Okay, something about Mike. Good, good. Thanks for telling me. All right, so now I know what bytes to avoid, and I can make my shellcode with MSF Venom. Same old thing. I get MSF Venom. I choose an attack of any type. I'm just going to use the simplest one, shell bind TCP, which will listen on port 4444. Here's the bad characters, 0, 9, A, and 20.
Wait, you changed the board that it was?
You can. You just put L port equals some other number.
Oh.
If you don't change it, the default value is 4444. And of course, 4444 is a pretty stupid choice because it's typically blocked by a firewall. You'd be better to really do a reverse shell. And a reverse shell to a local port of something like 443 or 80, where a lot of traffic goes to it. Yeah. Now you can't, this is a really weak attack because you're actually listening on their server, and typically that won't work because they only have official approved processes listening. And when you listen on another port, their firewall will not accept traffic. So this is just to show a proof of concept attack, really, like launching Notepad, not something of terribly valid. Anyway, so now these are the bad characters, and then I wanted in Python, this prepend fork equals true. If you turn on if you look at the advanced options for Metasploit exploits, there are about a dozen other things you can turn on if needed. And for some reason, it kept crashing on me, and I turned on this to make it quit crashing. You can make it fork a new process before the exploit or after the exploit, and there are like 4 different ways to exit from your exploit. And under different conditions, you need different ones. I don't really understand them. I just play with them until it works. But if you look at the options in your payload, that's why they're there. They're ones you need under certain conditions. And if you really were good at Unix and really understood exactly what was happening, you'd probably know why I had to do it. But I found by experiment that the exploit worked better with prepend fork equal true on. So this gives me 120 bytes of shellcode from Metasploit. So all I have to do is insert that in my attack. And that's what I've got here. So if I go to this one, if I nano F9, all right, this has got my address, same as before, and down here, here's my attack with my not sled and so on. And then I did have to put in a padding to keep the total length fixed. When I didn't do this, the location of the stack of the subroutine changed, so my pointer was pointing to the wrong place. So like I mentioned a long time ago, it's best to just keep your total attack length always the same. Otherwise, it will irritate you by having something change during your progress development. So I used to have 400 CCs. Now I have the real shell code and enough X's to add up to a total of 400. So the total length stays the same. So I run this one, F9, and say yes. And if I examine what's on the stack, it's a NOP sled, and this is that Metasploit shellcode, which is there, which is just going to look like random bytes. If I continue, it's going to not crash anymore, but exit normally. So it has exited, and because I did that fork, it launched another process, which is listing. So my original process called FS has now terminated. And if I go look, say here, I can do netstat minus pant, and there is now another process listening on 4444. Looks like I'm not seeing it here. Let me make my font a little smaller and my window a little bigger. And I see it up there. There you go. Even though I exited the debugger, there's still a process running listening on 4444. That's giving everybody control of my machine if they can connect to it. All they have to do, I can do it from another Mac shell out here, for example. We've done this before. I netcat into that machine, which is 192.168, 225.130 on 4444. Need a dot there. And now who am I? I'm root, ls, now I got a shell in the box to anybody that connects to that port. So that's fine. There's just a couple other little issues. But anyway, now before I proceed, I have to kill that process. So I'm going to use pkill to kill everything named fs. That's one way to do it. Now, if I do netstat, I'm no longer listening on port 4444. You have to free up the port before you can try it again, or it'll block you because the port's already in use. So now that was the exploit, and I ran it inside the debugger, and it worked. And hopefully you're getting used to this by now. It's not going to work outside the debugger. So if I run it outside the debugger, I do, might as well do it down here. Yeah, okay, I might as well quit from this. And that was F9, I think, what we were just doing. Let's see. Yep, that was F9. Okay, so this is the F9 attack. So to run the F9 attack outside the debugger, I do fs and this, f9.py. Same thing I was doing inside the debugger. And when I do it, I get a segmentation fault because GDB has hosed me again. GDP is not a perfect simulation of the real environment, and my pointer is wrong. I had to modify it, and there may be brilliant ways to do it, but I do it by trial and error. And what I found was adding 30 to it fixed it. So let's take a look at F9. And F9 here shows this address, BFFF F06C, but I had to change that to 9C, just adding 30 to it. Let's continue anyway. Okay. And there, I put a 9C there. Now it'll work outside the debugger. So F10, that now does not crash, but returns. And if I do a netstat minus pant, I see the 4444 listening again. So that's the same old mess. You may have to move things by up to 80 in hex. If you made a really big NOP sled, like maybe 300, and hit the middle of it, then it would cover this error. But even this NOP sled of 100 was not big enough to spare me from that error. Sometimes you have to add, sometimes you have to subtract up to 80 in hex. And I've read many learned treatises of why, but none of them have really been easy enough to remember. I've just gotten used to this irritating thing you have to do to refine your exploit to get it to work outside the debugger. All right. So there's my shell inside and outside GDB. And I've got some cahoots. And of course, you've got homework where you do this, but the cahoots are the next thing on the agenda, and we're just at the hour mark, so this is working pretty well. All right. So my cahoots are here. And if you're locked out, let me know. Okay. I think you've got a key anyway. You should be all right. So good. Okay. For people that are in CCDC, they're going to start a training upstairs now. I'll be up there pretty soon. I'm going to do these here cahoots first. My favorites. What's that? There is, CCDC is a defense challenge, and they're having training of some sort, which is new. And it's going from 2 to 5 today. So you can access it anywhere, but some people are watching it up in the lab. And that's where we're going as soon as this is done. I'll be up there just to make sure the lab stays open. Anyway, let me turn on the sound, and you can do cahoots. Okay. CCDC has been running for 10 years, but there never has been an official training program for it, which is very annoying. And now it looks like they're finally getting around to trying to do that, which is great because it keeps a lot of colleges out. There's no textbook, there's no agenda. You really don't know how to prepare your team. Everybody has to do what we did, join and lose horribly to find out how it works. And now you have a clue how to prepare, which is kind of unprofessional. And they're trying to address that now, I think, by having some kind of official training. I'll wait a few more seconds.
Are they training for people?
CCDC.
What are they training for people?
Yes. Well, I don't know. It's up to Liz. Liz is running the 140 Saturday morning class, and that's what's training for cyber competitions.
Oh.
I don't know if they train for Pico. They'll probably use Pico as a training tool for the other ones. All right. All right. So what defense will stop these format string bugs? None of them will save you. Code auditing is the only thing that will save you. It's easy enough to spot in the source code before you compile it, but none of these normal defenses do anything for you. So what's %D? All right, %D is just a decimal number. Let me see what this chat message is. What's the join code for students in Canvas infrastructure? Send an email to the class account, which is on my webpage here. If you aren't in the Canvas, send an email to this address, and my grader will send you an invitation to join the Canvas. So that's important. Good. All right. And all right, let's try another one of these. That's a pretty good face. All right, what's %P mean? Okay, that's a pointer. It will print the address of a string if you give it a string variable. How about %N? Yeah, that's the one that writes to RAM. I don't know why it exists, but it's very handy for us. All right, what happens when a program exits? All right, it calls the destructors, dstores, at the end. And so you could overwrite them to take over the machine. All right, so here's some winners. Let me make a note of these. Emmanuel and Peter D. Those are real names. The face. That's you. Okay, good, good. All right, I'll make a note. Anyway, all right. So I think that's it. Let me just point you to the homework. Of course, you're going to do this, and I see it pretty often in contests. So it's good to get sort of practice at this. Here's project 6 where you do it. I think there's an extra credit one where you do it also. So you just have to follow these steps and go through it. And one thing that's fun about format strings is capture the flag problems often have the easier version where you just have to read and not write. Because for one I did recently, I think it might have been in Pico, they had this thing, guess the number. And you have to guess this number, and you can't guess it. But what you can do is use the format string to read RAM to find where the right answer is stored, and now you know the number. So anyway, let's see what's here. Okay, thanks. Good. All right. All right. So I guess that's it. I'm going to go upstairs to the lab then and see what's happening with the CCDC training. And you're Danny, right? Good. Okay, good. All right. So I'll stop the share and go upstairs. All right. And